So now we're going to talk about mechanisms for heat transfer. And so this is ways that heat can be transferred. Earlier we talked about just amounts of heat that get moved, right? If you want to raise the temperature of something, you have to add a certain amount of heat to it. Heat is transferred from one place to another. But now we're going to look at how it's transferred and the rates. And so before we said things like Q is equal to MC delta T, or Q is equal to M L sub F. What we're going to look at now is how fast does the heat move? It turns out heat moves faster through some materials than others. Metals conduct heat very well. Insulators don't conduct it as well. And so we'll be looking at the power, which is the rate of heat flow, Q over time. You could write it as delta Q over delta T or something like that. Rates of heat flow and what the mechanisms are for that. And so there are three basic mechanisms for that, and you already know what they are. Probably learned them in middle school. One is called conduction. So do you have the rest of them now? Two is convection. And three is radiation. I'll sort of define them, and this is heat transfer by direct contact. When I put my hand on the board, heat is conducted from my hand into the board because my hand's warmer. Heat flows from hotter to colder. You might ask yourself why that's true. It never flows the other way unless you force it to, and it costs you energy to do that. Convection is heat transfer by motion of matter. So, for example, if you have a bonfire going somewhere, if I have some logs here, those don't look like logs, do they? But now I'm going to set them on fire. There we go. Right? And now you have warm air rising above the fire, right? This is convection. We would call this natural convection. But you can also have forced convection. An air conditioning system moves cold air into your house. It chills it in an air conditioner, and then it pushes it out into the vents in your house and forces it to go through the vents into different rooms. So you have natural convection and forced convection. Of these three, we have mathematics for these two, conduction and radiation, not so much for convection. And so when we get to convection, I'll do a little example of something, but it's harder to quantify these types of effects, or they're not easy to quantify, right? And finally, radiation is heat transfer by electromagnetic waves. Part of that comes from here, right? If you have a fire, it's producing infrared radiation, which is heating things up. And so when you have a bonfire, you get a little of all of them, I guess, right? There's heat transfer through the logs and into the ground by conduction. There's convection rising, warm air rising above the fire as it gets heated. And then there's radiation, the infrared, and some visible that's coming off this in all directions. Okay, so we're going to start with a little discussion of conduction. So let me just erase some of this stuff. I guess I'll erase all of it. We'll start with conduction. So heat transfer by conduction. And so that's where you have, something hot next to something cold. Oops, I lost my signal again. That's what happens when I erase. There we go. And so we're going to think of it sort of this way. I'll have a hot object over here. I'll label it T hot, and then I'll have another object over here, and it's I'm going to label it T cold, and then I'm going to have a bar going between them. Right, it's going to look like that somehow. Right, like that, and it connects them to each other, and it has area A. This is the thing that heat flows through, right? For these discussions, we'll assume that those two areas are the same, A, right? So the heat's going to flow through this bar that connects the two, right? The heat's going to flow from the warm object to the cold object. So it depends on the contact areas A. It depends on the separation D. It depends on the temperature difference. If there's a big temperature difference, you get a faster heat flow rate. If there's a small temperature difference, you get a low heat flow rate. And the thermal conductivity. So some materials are better at conducting than others. This is different from the heat capacity, which tells how much heat you have to add to something to raise its temperature by a certain amount. Remember, metals have low heat capacity, and so when you dump heat into them, their temperature goes up a lot. Insulators, water, has a high heat capacity, and so it takes a lot of heat to raise the temperature of water. You notice those things, by the way, when you go to the beach. The sand is really hot. It's a rocky thing. It's got a low heat capacity. The water is cool. The sun's shining the same on both of them. The water has a high heat capacity, so its temperature doesn't go up much, even though it's absorbing a lot of radiation because its heat capacity is so high. But now we're talking about thermal conductivities, and this is determined by how well heat flows through it, and it's a little different than the heat capacity. Although things with low heat capacities, like metals, tend to have high thermal conductivities. And so that's a little discussion about that. And so let's write the equation down for this. Right, let me erase some of this stuff, maybe just the words. It turns out that the power, which is the heat per time, is K A delta T over D. And this should make sense. This is just the thermal conductivity. So the greater the thermal conductivity, the faster the heat flow rate, the more power goes through. You can probably tell that the bigger the area are, the contact areas are, the more heat's going to flow. It's just like letting a larger pipe for water to flow through, right? The farther it has to flow, the longer the stick is, the lower the heat flow rate. If you put a mile bar between a hot and a cold thing, it would take forever for the heat to flow through it, and so it would slow it down. It's also proportional to the temperature difference. The higher the temperature difference, the greater the amount of heat flow you're getting through there. So let's do an example. So on a winter day, the temperatures just inside and just outside of a window are 5 degrees C and minus 10 degrees C. Notice this isn't exactly room temperature inside your house, but if you ever notice, right up against a window in the winter, it's actually quite cold just against the window, depending on how good your windows are. In this case, we've got a single paned glass window, which is not very typical. So it's 5 degrees C inside and minus 10 degrees C outside. If the window has an area of 3 square meters and a thickness of 0.635 centimeters, or that's 0.0635 meters, right? 0.635 centimeters is 6.35 millimeters, which would look like that. And the thermal conductivity is 0.84 joules per second meters degrees Celsius. What is the rate of heat flow through the glass? And so we have to come up with our formula here, which is the power is equal to K A delta T over D. And so I just have to plug all those in, right? This is 0.84 joules over seconds meters degrees C times my area, which is 3 meters squared, times my temperature difference. And usually we do outside minus inside. And so it's minus 10 degrees C, minus 5 degrees C. This doesn't matter too much because you're going to know that the heat's flowing from the hot one to the cold one. Here, the minus sign that we're going to get on this is going to indicate that the heat's leaving the house, right? Which is what you expect it to do. And then the D, right, the distance, the bar is actually just the thickness of the glass, right? The heat's flowing through from the inside to the outside through the glass. And so this is 0.00635 meters, I believe, like that. And what I get for this, let's just work the units here for a second, because I pulled up these units for this thermal conductivity, and we have to just see that it works, right? These guys are in degrees Celsius, and so the degrees Celsius are going to cancel. That's going to be a minus 15, right? And the degrees Celsius are going to cancel. And then I have a meters in the denominator, and a meter squared in the numerator, and then I have a joules and a seconds. And so the number I get is about 5953 joules per second, or 5953 watts. So that's, a 3 square meter. That's a big window, right? It's a big picture window, but it's losing an enormous amount of heat. You could cut way back on that if it was a double paned, because then the heat would have to flow through the air gap in between, and it has a much higher heat much lower thermal conductivity than the glass does, and so it would greatly reduce the heat flow. And so usually in areas where you have in windows, for example, rather than just having a single piece of glass that the heat flows through, you have a double pane glass with an air gap, and that cuts this number way down. Okay, let's do another one. So here's another problem. You stand with 1 foot on wool carpet, which just has a thermal conductivity of 0.004 joules per second meter degree C, and 1 foot on ceramic tile, which has a thermal conductivity same as glass, 0.84 joules per second meter degree C. The area of each foot is 80 centimeters squared, which is, I have to multiply that by 10 to the minus 4 meters squared per centimeter squared, and so that's going to be 0.0080 square meters. Right? So you stand with 1 foot on wool carpet, which is thermal conductivity of 0.004 joules per second meter degree C, and 1 foot on ceramic tile, which has this thermal conductivity. The area of each foot is that. If the tile and carpet are each 2 centimeters thick, at what rate does each foot have to produce heat to maintain their 33 degrees C temperature, that is the temperature of the foot, if the slab is at 10 degrees C? So I'm going to draw a picture of a foot just so we kind of agree. Right? I know this isn't a very good foot, but that's my foot, right? And so what we're saying here is this is the bottom of my foot, and its temperature, we'll assume it's in contact the whole way, is 33 degrees C, right? And now this is the thing that's 2 centimeters thick, right? And it's either carpet or tile, depending on which foot you're talking about. And then underneath that is the slab, and down here, this is T equals 10 degrees C, right? And what we're saying is heat's going to flow through here at some rate, and your foot needs to supply that same rate of heat to your foot so that it doesn't get cold. And so we're basically asking, what's the heat flow rate through this region, because that tells how much heat your foot has to keep supplying to keep your foot from getting colder. Right? And so once again, this is a thermal conductivity equation. And so they both look like this. P equals K A delta T over D, right? And so if I do the ceramic one first, I'm going to erase this drawing, my beautiful drawing, right? If I do the ceramic tile first, I do K tile A delta T over D, and that's 0.84 joules per second meter degree C times 0.008 meters squared times the temperature difference, which is, if I do out minus in, it doesn't really matter. This is 10 degrees C minus 33 degrees C all over the thickness, which is 0.02 meters. And so what I get for this one, power for the tile, is minus 7.7 watts about. I think in the last example I should have had a minus sign and I didn't. So you can go back and check that for me. I'm not too worried about the signs on these things because you know it goes from hot to cold. And so that's not such a big concern. And so so what we get is the foot that's on the tile has to supply 7.7 watts of energy to the foot to keep it from getting colder, because that's how much is being conducted away all the time. And now if we were to switch and talk about this foot, right? In fact, we can almost just look at this thing and say, well, what's different? The temperature change is the same. The thickness is the same. The area of the foot is the same. What's different is the thermal conductivity. And this guy isn't 0.004. That's my mistake. It's 0.04. So let's just correct that before we do a calculation with it, right? And so if you look, this times 21 is that. And so my answer is just going to be 21 times smaller. And so P for the carpeting is P for the tile over 21. And what I get for that is about 0.37 watts. Boy, I used every bit of the board for that. Right? Since the only thing that's different is the thermal conductivities, and this one is 21 times smaller than this one, it means that this power is going to be 21 times smaller because all the other numbers are the same except the thermal conductivity. And so instead of giving 7.7 watts, I divide that by 21 and get about 0.37 watts. Okay. So I wanted to say a couple more things about heat flow by conduction. So normally we've written it this way. We've written it as K A delta T over D. Sometimes we'll write down a resistance to heat flow. Oops, I did it again. Here we go. Sometimes this will be written this way, and this is our definition for heat flow by conductivity, by conduction. And sometimes it'll be written this way. It's the temperature difference divided by the resistance to heat flow, where the resistance is D over Ka. Right? And so they're the same equation, but you write the power is equal to the temperature difference divided by the resistance to heat flow. And that kind of sort of has a sensible thing. The greater the temperature difference, the greater the heat flow rate, the greater the resistance, the smaller the heat flow rate. And so our resistance looks like this. And you can sort of see that a good thermal conductivity makes the resistance get smaller. A big area makes the resistance get smaller because it's easier to heat flow. A smaller distance makes the resistance get smaller. A larger distance makes the resistance get bigger. A smaller area makes the resistance get bigger. And so this does sort of look like a resistance. And so so it's often written this way. And then you can look at some examples, like once again, let's do a 2D version of this, so I don't have to do the fancy 3D drawings. And I can say, look, this is my T hot, right? And this is my T cold over here. And I have two materials. This material has thermal conductivity K1, and this has K2, right? They both have the same. Well, let's say they have the same area, right? And this is D1. Sorry, D2, and this is D1, right? And we can ask, well, what's the resistance of the combination of these two, right? It's hard to do it here. We don't know what this intermediate temperature is. This borderline could be anywhere. D1 could be really big relative to D2 or really small. But what we do know is that the total power, that is the power flowing from the heat rate flowing from T hot to T cold, is equal to whatever's flowing through this one and whatever's flowing through this one. In other words, every joule of energy that goes from here to here passes through this one and passes through this one. It's not a different rate of heat flow through here than through here, because every one of these guys has to go through this guy to get to here. If these were cars and these were sections of highway, if the cars have no way to get out in between, then every car that goes through K1 has to go through K2, and you can think of the heat that way also. So P tote is equal to P1 is equal to P2. I can say the total temperature across the whole thing, delta T, is TH minus T cold, and that's equal to delta T1 plus delta T2, right? The temperature across the whole thing is the temperature drop across here plus the temperature drop across there, right? And so I have delta T1 is equal, delta T total, I'll just call it delta T, is equal to delta T1 plus delta T2. But now I can use this equation to say, look, this is just P total times R total, because delta T is P times R, is equal to P1 R1 plus P2 R2. But we said all the P's are the same. And so that means the total resistance for conductors in series is just the sum of the two resistors in series. So if I determine the resistance of this guy, right, R1 is equal to K1A over D1, and R2 is equal to K2A over D2, then the total resistance of these two guys is just the sum of those two resistors, right? And we say they're in series because it's one after another. This is analogous to circuitry. So resistors in series just add. This is just like in circuits. Okay. So now let's look at a different one, similar but different. Here's T hot and T cold. Now I have two different thermal conductors, this one and this one. I'm purposely drawing them different. This is K1 and this is K2. Maybe they're the same distance, but they have different areas. They wouldn't even have to be the same distance, really. But we call these in parallel because heat can flow through both of them at the same time, unlike the other one where it has to go through one, then go through the other, the same heat, right? The ones that are in series. And so with these guys, we can say, look, delta T1 is equal to delta T2 is equal to just delta T, right? The temperature difference across this guy and the temperature difference across that guy, and the total temperature difference is the same, right? Also, we know that the total power is just the sum of the two powers, right? Can we agree on that? However much joules per second is flowing through this one, plus the number of joules per second flowing through this one, has to add up to the total joules per second flowing across. Right? And so now I can say, look, P tot is delta T over R tot, right? And that's equal to P1 plus P2, which is delta T1 over R1 plus delta T2 over R2. But remember, all of these delta T's are the same because they're all connected across the same, all the way across the hot and the cold. And so this just becomes, I can cancel in this equation here, I can cancel all of the delta T's because they're all the same, and I get 1 over R tot is 1 over R1 plus 1 over R2. That is to say, the total resistance inverted is the sum of the inverses of all the parallel resistances. This is very much going to look the way we do resistance in circuits. All right, that's probably a good stopping point.